All right, hey everybody, this is Mr. Perry, and I wanted to take you through some common base conversions for different number systems that you're going to need to be familiar with in AP CSP. So in order to get there, we're going to start with the most familiar number system that we have, which is a base 10 system. And I'm setting this up like the flippy-do so that you kind of get, a familiar context with which to look at number systems. Anytime you have to do a number system conversion in my class or on the AP exam, then it's kind of useful to think about the flippy-do because this is a tool that you've already learned in order to understand binary. And you can basically put any number up here and just kind of change the look of the flippy-do and look at, again, number systems this way. So this is what was, in the flippy-do, it's usually 2 to the 0, 2 to the first, and so on and so forth. Here's our base 10 system, and of course, if we are in that base 10 system and we start counting, then we know that we can count from 0 all the way up through number 9. So we're just going to do that real quick, as fast as this program's going to let me. And once we get to 9, we run out of digits, and so we have to go to 10, and it looks a little bit more like this. So we are already super familiar with counting in this number system. We know that basically this would be 19,507,182. We're used to looking at numbers as basically strings of numbers like this. But just remember that, a long time ago, probably in elementary school, you looked at numbers in different columns. We talked about the ones column, the tens column, the hundreds column, the thousands column, and so on and so forth. So this is called the base 10 number system, also known as decimal. We use a decimal number system. So that changes when we get into the field of computers. Now we're looking at binary, which is a base 2 system, right? And we can only count up to 1. We can count from 0 to 1, and then we have to start using the next column. So this would be the number 3. This would be the number 5, because we have one value of 4 and one value of 1, and so on and so forth, right? So this is also, we're familiar with this. It's the base 2 number system, and if we have a whole byte of data, then we know we can count all the way up to number 255, which is why the number 255 is so commonly used in this particular class. Okay, so at this point, we are familiar with going from the decimal base 10 system to the base 2 or binary number system. Well, that's not all we need to know in this class. You do have to just kind of look at this as your starting point. You want to be really comfortable converting base 10 to base 2, and you want to be really comfortable going from base 2 to base 10. You should be able to easily go from, if I give you the number 102, you should be able to plug that into the flippy-do fairly easily and figure out what would be the binary for that. And vice versa, if I gave you 11010111, you should be able to plug that into the flippy-do and figure out what the normal, base 10 system would be. If not, go to the class schedule and look for the binary number games and, just kind of play around with it until you get a little bit more familiar. Now, the reason why we have to talk about this is in the field of computer science, every once in a while, we use other bases. So like there's this thing called octal, which is a base 8 system. And then there's another thing called hexadecimal, which is a base 16 system. And so it's useful to think about that flippy-do and how you would change it if you wanted to work in some of these different bases. Like, what if it was a base 5 system? What if it was a base 8 system? Now today we're going to look at hexadecimal because this is one which is super common. Now if you changed the flippy-do to look like hexadecimal to be a base 16, you wouldn't have 10s or 2s up here. You would have 16s, right? And this would be 16 to the 0, which would give us about a value of 1, and this would be 16 to the first power, which is a value of 16. Now the good thing about hexadecimal is this is as far as you need to go, all right? And we'll get into why in a while. Now when you count in a base 16 system, you count like normal. you go all the way up to 9, but then what happens is, you can only put a single value in each one of these columns. So when you get to number 10, you can't put 1, 0 in here. You need a single character value for the number 10. So they actually use A for 10, and then B means 11, C means 12, and we keep going. D means 13, 14 is E, and then 15 is F. So this is as high as we count, because if we wanted to represent 16, then 16 is represented as 1, 0, right? Because you would have one value of 16, which means you now need 0 values of 1, and then 17 would be 1, 1, and so on and so forth. So this is the base 16 number system, also known as hexadecimal. So if you wanted to go all the way up to 255, you do FF, because as it turns out, 15 times 16 plus 15 times 1 does equal 255. So this is one of the reasons why hexadecimal is very useful for us. When we talk about why we need this, it's a lot easier to look at FF and say, oh, that's the number 255, as opposed to thinking about 1, 1, 1, 1, 1, 1, 1, 1. This is just a lot more clunky. This is a little bit more succinct. So that's basically why it's important. It's also important in this class because it's widely used to represent RGB color. So hexadecimal is associated with RGB color. And then it's actually also used with IPv6 IP addresses when we talk about the internet. So let's talk about converting binary to hexadecimal. I'm going to show you the easy way, and if the easy way works for you, then this is really all you need to know. But if you want to understand it at a deeper level, I'll also explain it the hard way or the longer way. So if you get a string of 8 bits, and if you have to convert those bits to hexadecimal, the easiest thing to do is to take the first 4 bits, 1, 1, 0, 1, and then separate that from the second 4 bits, 1, 1, 1, 1. Now look at each of these as the first 4 columns of a flippy-do. So this would be the 1's column, 2's column, 4's column, 8's column, right? So 1, 8 plus 1, 1 is 9. So that's this part right here. And then the other 4 bits, 1, 1, 1, 1, we recognize as 15. So now all you have to do is take this first 4 bits, which is 9, and say, well, what is that in hexadecimal? Well, that's just the number 9. Now, the second set of 4 bits is 15. Well, 15 is actually represented by letter F. So the quick and easy way of going from binary to hexadecimal is to just split it in half, look at the first 4 bits and then the second 4 bits, convert those to decimal, and then replace the decimal with their hexadecimal values, right? So 9F. Here it is again. Here's another one, 1101, 0011. If I convert that to hexadecimal, I split it in half. 1101, let's see, that's 8 plus 4 plus 1 equals 13. 0011 is 3. Okay, well, I can't say 13. I have to use letter D when I'm in hexadecimal, and then 3 is still 3. So the hexadecimal value for 1101.0011 is D3. Now this is the longer version of it. Let's talk about, on a deeper level how this works. And at this point, if you're good, just go ahead and turn the video off. But if you want to understand this at a deeper level, this is basically what's going on. That same bit string, 1101.0011, if we took the whole thing and converted that to decimal, it ends up being 211. If you plug that into the flippy-do, it's 211. Well, if you want to figure out, well, how many times does 16, because remember hexadecimal has 2 columns, a 16's column and then a 1's column. So the first thing you have to do is figure out, well, how many times would 16 divide evenly into 211? Turns out that number is 13. So, 13 is D. And then the remainder, when you do 16 times 13, that takes you to 208, so that means there's 3 left, right? So the remainder is 3, which we know is just 3 in hexadecimal. So 16 times 13 is, gives you the first part, and then 1 times 3 gives you the other part. You add that together, and so D3 is the hexadecimal version of this bit string right here. And I think at this point, I'm just going to take you back to this really quick. Again, D3 worked for that because the first value is multiplied by 16, and then the second value is multiplied by 1. So, D3, 13 times 16 was 208, and then 3 times 1 is 3, which takes you up to 211. So that's, again, how those hexadecimal values work. So if we take that to the value of color, here is a super zoomed in picture of the Facebook logo, and just remembering that every pixel on the computer screen is broken up into red, green, and blue values. Here is where we start talking about color. So one color is given 1 byte from 0 to 255, and 1 pixel of RGB color is 3 bytes. So you have a value from 0 to 255 for red, 0 to 255 for green, 0 to 255 for blue. So if you looked at a bit string, here's 24 bits. When you divide them up into 3 sections of 8, here is the binary value for the red, here's the binary value for the green, here's the binary value for the blue. So these are all numbers between 0 and 255 telling the computer how bright you want those channels, the red, green, and blue channel, to go. So again, looking at this in terms of hexadecimal, if it's all zeros, we know it's black, and it turns out if we take each channel all the way up to 255, it's white. Anything in between, as long as the numbers equal one another, will be on grayscale. But if you go FF on your red channel, that means you're at 255 for red, so you're bright red, but you've got 0 for everything else. So that's all you see. You're just seeing the red lights in this section. If you do FF and your green channel, then that's, again, 255 right here. And that maxes out the green lights and all of the pixels right here. And if you want FF over here, you're maxing out your blue channel. And again, there you see obviously bright blue. If we dim the lights in these different colored bars right here, here's again FF, so that's 255, but 80 would be 8 times 16 plus 0 times 1. So whatever 8 times 16 is, that's how bright these red lights are. And then 33 is, okay, 3 times 16 plus another 3. Again, you do the math, whatever that number is. You can see right here, it's kind of a maroon. It's a really super dark, super dull red. So the same thing's happening here. FF is 255 for your green. 80, whatever that value is in hexadecimal. Again, you can do the math, but here that is kind of middle green, and then 33 is even duller than that. And here's the same thing happening with blue. And then also when we blend colors, if you do max red and max green, you get yellow. If you do max green and max blue, you get this kind of aquamarine color. And if you get max red and then max blue, that gives you bright, bright purple. So in general, like I say, it's important that you can comfortably go from binary to decimal. And then it's important also that you can go from binary to decimal to hexadecimal, but it turns out there's actually an easy shortcut to go from binary to hexadecimal. So hopefully this helps make a little bit more sense. There are lots of games and tools that you can use online to familiarize yourselves with RGB color a little bit more and understanding how hexadecimal works. I think that's it for now. So thanks for watching, and I will see you in class.